Welcome again to Terra Physica channel, and today we're diving deep into one of the most intriguing mysteries of modern physics that has been baffling scientists for generations, both theorists and experimenters alike. Solving this puzzle could unlock secrets about our universe's past, present, and future. But for now, it remains a tough nut to crack in the world of physics. So, hit that subscribe button and let's get started. Now, everything around us, and I mean almost everything in the visible universe, is composed of just three types of particles: protons, neutrons, and electrons. Protons and neutrons make up the nuclei of atoms, while electrons form outer shells, sticking around thanks to electromagnetic forces. But here's the kicker: just 100 years ago, the prevailing belief was that there were no other elementary particles out there, excluding interaction carrier particles like photons and their pals, but we'll tackle that another time. However, that idea took a sharp turn. With the advent of new observation tools, scientists began discovering a plethora of new elementary particles, starting with dozens and soon soaring to hundreds. The simple and elegant view of a world made up of only three types of particles went out the window. However, order emerged from the chaos fairly quickly. It turned out that particles like protons and neutrons weren't elementary themselves; they were made up of even smaller components called quarks. Most of these newfound particles, akin to protons or neutrons, known as baryons, turned out to be composed of just 6 types of quarks, grouped together in 2s, 3s, and occasionally 4s or 5s within a single particle. Then, there's the electron, a lone ranger without internal structure, and its heavier siblings, the muon and tau leptons. They're pretty similar to each other, differing mainly in mass. The muon is about 200 times heavier than the electron, while the tau lepton is roughly 17 times heavier than the muon. At the same time, the vast majority of these particles are unstable. And not just a little unstable, often they exist for mere fractions of a second before decaying into lighter particles. As an example, let's consider the lambda hyperon, specifically the neutral lambda hyperon. It's made up of an up quark, a down quark, and a strange quark. On average, after just 2/10 of a second, it decays into either a proton and a negatively charged pi meson or a neutron and a neutral pi meson. Now, the negatively charged pi meson, it has a lifespan of about 26 billionths of a second, before decaying into a muon and an anti-muon neutrino. And finally, the muon itself lasts around 2 millionths of a second before decaying into an electron, a muon neutrino, and an electron anti-neutrino. The neutral pi meson's existence is even shorter, roughly 8.5 by 10 to the power of minus 17 seconds. After that, it either transforms into 2 photons or into an electron-positron pair. Speaking of which, the term decay isn't a perfect fit for describing the behavior of these particles. Decay implies that the initial particle contains bound particles that become reaction products, and the process involves breaking those bonds and releasing them. That's not the case here. The lambda hyperon doesn't consist of a proton and a pi meson, and the pi meson doesn't contain muons or electrons. It's more accurate, perhaps, to describe it as a transformation of one particle into another or a combination of different particles. However, historically, decay has stuck to this process, partly because these processes involve a decrease in mass. Heavier particles become lighter, those become even lighter, and so on, until it all ends with the lightest of them all: protons, neutrons, and electrons. So, while there are hundreds of particles in reality, in our everyday experiences, we mainly deal with just 3, our trusty, relatively stable protons, neutrons, and electrons. Oh, and don't forget neutrinos. These nearly massless, chargeless particles are byproducts of particle interactions, and they seem to be pretty stable too. The thing is, due to their tiny mass and lack of electric charge, neutrinos are extremely challenging to detect. Still, every second, about 50 billion neutrinos pass through every square centimeter of Earth's surface. While an individual neutrino is almost weightless, their combined mass in the universe could be substantial, perhaps even comparable to the total mass of protons, neutrons, and electrons, if not more. And with the evolution of the universe, this balance might shift in favor of neutrinos, as the number of these particles increases over time. And here is the question: how stable are protons, neutrons, and electrons themselves, and can they also undergo any transformations? Neutrons, for instance, actually can. Their mass is about 0.1% greater than that of a proton, and on average, after about 14 minutes and 38 seconds, a neutron turns into a proton, an electron, and an electron antineutrino. Though these transformations happen to free neutrons, within atoms, neutrons can have much longer lifetimes, sometimes even unlimited. And once again, it all comes back to a fundamental principle: the mass of an object, in this case an atomic nucleus, should be less after a transformation than before. Let's take a look at stable, electrically optimized carbon-12, with 6 protons and 6 neutrons in its nucleus. Its atomic mass is 1.993 by 10 to the power of minus 23 grams. Now, suppose one of its neutrons transforms into a proton and an electron. This process is called beta decay. The result is carbon-12 transforming into nitrogen-12 with 7 protons and 5 neutrons, and the mass of this atom turns out to be 1.996 by 10 to the power of minus 23 grams. So, even though a neutron transformed into a lighter proton through beta decay, the total nucleus mass increased. That's because a nucleus's mass isn't just the sum of the masses of its particles. Now, sometimes the reverse can happen. The conversion of a lighter proton into a heavier neutron actually decreases the atom's mass. For instance, in carbon-11, which has 6 protons and only 5 neutrons, the atom's overloaded with protons, or underloaded with neutrons. This tends to cause one of its protons to turn into a neutron, releasing a positron, the antimatter counterpart of an electron with a positive charge. This process, called beta plus decay or positron decay, transforms carbon-11 with a mass of 1.829 by 10 to the power of minus 23 grams into boron-11 with a mass of 1.828 by 10 to the power of minus 23 grams. So, while a proton transforms into a heavier neutron, the nucleus mass ultimately decreases. Now, when it comes to individual particles outside atoms, a neutron can transform into a proton since it reduces mass. However, a proton can't transform into a heavier neutron. But could it undergo other transformations? Well, we can't say for sure, and that's the very enigma of physics that this video aims to explore. Now, let's talk about electrons. They're incredibly stable. Experiments have shown that throughout history, there's been no observed decay of an electron or its antimatter counterpart, the positron. Furthermore, electron and positron stability has a fundamental theoretical basis. These particles are the lightest of all charged particles. Charge conservation law is one of the 4 fundamental laws, alongside the laws of energy, momentum, that's the quantity of motion, and angular momentum, that's the amount of rotation. So, this law can't be violated during particle transformations. Since there's no way for an electron to decay into something while keeping the total charge unchanged, we're confident that electron or positron decay is impossible. Why are we so confident in the conservation of charge? Because, like all the other laws, it directly follows from the universal symmetry of our world. For example, the conservation of energy law arises from the homogeneity of time, that is, processes in the universe unfold at the same fundamental speed. So, if that muon we mentioned earlier decays in 2 millionths of a second today, it'll still decay in 2 millionths of a second a year from now, 1,000 years from now, and even 1 billion years from now, and conversely, it was decaying at the same rate 1 billion and 10 billion years ago. The conservation of momentum stems from the homogeneity of space, which means all physical processes follow the same laws on Earth, on the Moon, on Alpha Centauri, or even in the MAX 0647 JD galaxy, 13.3 billion light-years away from us. And the conservation of angular momentum, the very law that keeps a spinning top upright, arises from the isotropy of space, the absence of privileged directions. No matter where we look, we'll see the same space with the same physical laws. Charge conservation law is rooted in a more intricate symmetry, what we call gauge symmetry. The intricate dance of why fundamental conservation laws stem from space symmetries is the playground of field theory, a subject that haunts physics students' nightmares for years. Yes, it still pops up in my dreams from time to time, and if you'd rather avoid another reason for sleepless nights, just take my word for it. So, electron decay is a no-go according to the fundamental law of charge conservation, making us confident it won't happen. But when it comes to proton decay, there's no such law that forbids it. Theoretically, a proton could change into a positron and a neutral pion. Notice how the electric charge of the reaction products equals that of the original particle, making this reaction possible. And in the realm of quantum physics, if something is theoretically possible, it's bound to happen from time to time. Here's the scoop. Based on our current understanding of the universe, protons should fundamentally be unstable and occasionally break down. Of course, they do it very rarely. Theoretical estimates suggest a proton's lifetime should be at least 10 to the power of 30 years, or 100 billion years. Just to put that in perspective, the current age of the universe is around 13.8 billion years. Now, bear in mind that when we discuss the lifetime of a particle, we're always talking about average lifetime. The decay of elementary particles is a probabilistic process. As we mentioned before, the average lifetime of a free neutron is about 15 minutes, but that doesn't mean every single neutron will decay after exactly 15 minutes. One might decay after a second, another after a minute, another after an hour, and some might even last a million years, though that last scenario is quite unlikely. Similarly, with a proton, the statement a proton's average lifetime is 10 to the power of 30 years should be understood probabilistically. If we were to observe 10 to the power of 30 protons for a year, we'd have a decent chance of witnessing a couple of decays if the average lifetime indeed holds true. Now, 10 to the power of 30 protons might sound like a lot, but it's roughly the number contained in just 1 ton of regular water, occupying a cubic meter of space. In simpler terms, if we surround that volume of water with sensitive detectors and observe it for a year or two, we should catch at least a couple of those proton decay events. Scientists have made numerous attempts to detect proton decay. The most impressive setup for detecting proton decay is the Japanese detector called Super Kamiokande. It's been observing a reservoir filled with 50,000 tons of water in an old zinc mine, a kilometer beneath the Earth's surface, since 1995. Unfortunately, they haven't spotted a single proton decay event yet. So, here's the paradox: theoretically, proton decay should happen, but practically, we can't seem to catch it in the act. There are two possible explanations for this. The simplest explanation could be that protons might just have a longer lifetime than previously thought. For instance, if the proton's lifetime is on the order of 10 to the power of 35 years, the lack of results could be explained by working with too small quantities of matter or not waiting long enough. That's why scientists are planning to deploy even more powerful detectors. The second, slightly more baffling explanation could be that we aren't detecting proton decays because, contrary to our expectations, they just don't happen. If that were the case, it would mean there's a fundamental conservation law prohibiting this decay, and thus, an unknown fundamental symmetry of the universe. Either way, most scientists today still lean towards the idea that proton decay is likely. Based on experimental results, or more accurately, the lack thereof, the minimum possible proton lifetime is estimated to be around 1.6 by 10 to the power of 32 years. This means that practically all the protons making up the matter around us will decay in roughly 10 to the power of 35 years. At that point, the familiar matter we know will cease to exist. No more stars, no more planets, just an endless sea of gas made of electrons, positrons, and neutrinos, swirling around islands of black holes, the only compact objects that will persist into that distant era. But as for how physicists envision the far future of the universe as a whole, we'll delve into that in more detail another time. So don't forget to subscribe to the channel, so you're always in the loop for some fascinating stuff.